Thanks. Good morning. I'm going to talk a little bit about what we know is happening in the Arctic and touch on a few of the things that we don't know about. This is surface observed temperature field in 1884. This is a compilation of all the measurements that those Victorians and friends did back then. Actually, it's good data. And we're going to look at how these data run forward in time to the present day. Are you ready? By the way, the yellow spots mean warmer than average, the blue spots mean cooler than average over the period. Okay, here we go. Here we go, forward in time. So as you can see, the world is warming up. You'll see more yellow appearing. But you also see something else happening in the northern hemisphere if you watch carefully. Coming into the 1950s now. 70s, acceleration in the 80s. And that's today. So, okay, it's warmer everywhere, as you can see, just about, but it's 2.5 times as warm as the global average in the north. And that's because of the sea ice albedo feedback. So every time I melt a nice white piece of ice, I expose black seawater, that absorbs the sun's rays better, it warms up the water a bit, it melts more ice. Pretty obvious, huh? Okay, so what can we see? Hey, Merritt, can you bang the button? I think this has run out of oomph. Okay. All right, we've been using a satellite to track Arctic sea ice extent, just the area, not the thickness, all right, since 1979. This is a microwave instrument. It works through clouds, it works in the dark, and it tells you the aerial extent of sea ice. Now, we're looking at the minima at the end of the summer and tracking that over time. And you can see we start out at about 6.5 million square kilometers. And then recently we get a bit of a nosedive. There we go. It's one. And another. Bit of a rebound. And we're waiting to see the numbers this year. So it turns out that this downturn was underpredicted by our models the last time around in IPCC AR4. And there's been some corrections done to the latest round of models, but still this was a surprise. This is sea ice area. It's not, doesn't say anything about thickness. We don't know really enough about thickness, and we won't know until we get our satellite up there with a LiDAR that can measure ice thickness. So that's coming up in 2016, 2017. Next slide, please. Okay, just to sort of give you an idea of the complexity of this system. This is the same satellite microwave data phased over time and during the seasons. You can see it shrinking. It's kind of like a great sort of octopus or something. It squidges itself around between all the channels. It moves around with currents and with wind fields. It's quite a complicated process. However, raw energy drives the total extent for the most part. Though you can find on some years when the wind pattern's different, this stuff gets piled up against one edge of the ocean or the other. By the way, at the start of the observation period, we had large fields of what we call multi-year ice. That was ice that had been there, 4, 5, 6 years old. Now there's very little of that left. The ice that we have is this year's ice or the previous year's ice, and not much older than that. Next slide, please, Merritt. Okay, just showing the wind fields that push around the ice. We can use general circulation models that describe the wind fields very accurately and also the air temperature fields. And this gives us a very good handling on being able to check our satellite measurements and do a better job of modeling sea ice. Sea ice thinning is still a problem. We don't know really how to model that. We're working hard on it. So a whole lot of, the university community, NASA, NOAA people, we're knocking ourselves out on that. But we have the tools, as you can see. This is a general circulation model with a coupled ice, ocean, atmosphere system. All right, so last thing I'm going to talk about is new technology for measuring how much ice we have. This is the GRACE satellite system. These are 2 satellites that fly around the world several hundred kilometers apart, not like that, in other words. And they track the distance between them with a radio beam to within 1/100th the width of a human hair. They know the separation between them. Every time the lead satellite goes over a large ice mass, it gets accelerated. A large sort of dense mass on the surface, it accelerates away from the trailer. And likewise, when the other guy catches up with it. By doing a whole lot of math, you can figure out the gravity anomalies on the Earth's surface, and that way you can tell changes in ice. You can actually weigh the amount of ice on Greenland and Antarctica. Next, please. So what did we learn? Okay, for Greenland, since the period of record, since GRACE was launched 2003, what we see is that the ice declines, the ice melts in the summer. You get a bit more top up in the winter with snowfall, then it goes down the summer. But notice how that the trend is overall downwards. Okay, watch that. Okay, so you're wondering what the units are on the, what is a gigaton of ice? You're looking at about 1,000 gigatons of ice disappearing there. A gigaton is 1 cubic kilometer of ice, which is a very large block of ice. All right? So there's 1,200 gigatons have fallen off Greenland into the ocean. Next, please. We had a LiDAR satellite up there that was measuring ice thickness, and it conked out a few years ago, and we're busy building a replacement. Until then, we're forced to use aircraft to try and fill in the data gap. So we have this thing called Operation Icebridge, 2 aircraft going to the North Pole and the South Pole every year in Greenland, and mapping the ice fields with LiDARs. We can't cover the same area that we could with a satellite, obviously. But this is the best we can do during the gap, and that's why it's called Icebridge, because it's a gap between 2 satellites. Next, please. So what we're working on here is this is ICESat-2. This will launch in 2016 or 2017. It's a 6-beam LiDAR system that will not only tell us the thickness of the ice and the extent, but also we'll be able to work out velocity of ice, so how fast it's moving. So glacier movements we'll be able to get out of this as well. And I think one more, and I think I'll stop. Yeah, this is a good one. So this is ice mass balance. We're using different methods, independent methods, to figure out how much ice is being lost. Let's see, going to the top is input-output model in red, radar altimetry, laser altimetry, and GRACE, which is that gravity system. Completely different physics, or mathematics in some cases, for these estimates. GRIS is the Greenland ice sheet. That's that 200 gigatons a year that I was telling you about. Then you go all the way down to East Antarctic ice sheet, and then the total of everything, Antarctic ice sheet plus Greenland ice sheet on the far right. Estimates diverge a bit, but they're still centering around 300 gigatons a year. We're going to hopefully sharpen that up with better observations in the future. So there you go. We're losing ice everywhere. In Antarctica, it's a bit more complicated. There's some small gains in some places, larger losses in the other places more recently. But we've got the goods and the tools, basically, to track this pretty well. And we're going to keep a close eye on it towards the end of the decade. Thank you for your attention.